Hello everyone. Today we are on board to present a topic called Battery Management System. This video series is presented by myself Manikanta, Ekta Chirde, Parikshit Kathwate and Avinash. So whenever we talk about the battery management system, first we will see why a battery monitoring system is required. So coming to the battery monitoring system, this battery, we know that the battery monitoring system consists of a series of lithium ion cells having different voltages across their terminals. These tiny cells are connected in parallel and series combination. These tiny cells are very dumb and highly unstable. The voltage across the cells has to be precisely monitored and balanced. If we don't do so, then we won't be able to come up with the battery pack, and destroying the battery pack will be the ultimate thing. In this, as we are going to discuss about the electric vehicle, if we are not doing this in respect to this, so when a battery is charging, we have to apply the voltage and current to it. If this voltage is more than the specified limit mentioned in the data sheet, then it is considered that the battery is charging with over voltage, which will eventually increase the temperature of the battery. Every battery has a specific range of temperature in which the temperature in which the battery works fine. So this temperature increases, which ends up in reducing the state of charge. This condition also increases the internal resistance of the battery and eventually the power loss across the battery increases. On the other hand, if the voltage applied in the battery is lower than the also it lead to over temperature. Over voltage and under voltage lead to a temperature which degrades the battery life, and if we use battery at a temperature lower than its specific range, then its capacity decreases. Due to this, the old temperature, the batteries might catch up with fire, as well as there is always slight differences in the state of charge and the charge rate capacity impedance between two cells, even if the cells are from same manufacturer and produced in the same lot. While charging or discharging these cells altogether, some cells experience a lot of stress in the battery pack, so they lead to degradation. Well, to avoid all these scenarios, we must have to monitor over voltage and under voltage limit of the battery. We have to keep a close watch on battery temperature, and we have to ensure that the charge level of each battery stays within the recommended range by balancing every cell so the efficient in effective way. Here first comes the discharge control. Batteries healthy first is the discharge control. The primary goal of a BMS is to keep the battery away from operating out of its safety zone. The BMS must protect this during the discharge. And the second comes the SOC determination. In this, the user about to current capacity of the battery can be known, and the battery, there are several methods to determine the SOC, so that the SOC can be determined through two ways, the direct voltage measurement and Coulomb counting, and the third way is the combination of Coulomb counting and voltage measurement. Well, there are different types of determination of SOC methods, but we will be focusing mainly on the first two. In this, the discharge cycle of the battery is associated. The battery voltage decreases, the battery also decreases in the Coulomb counting method, and the current coming in or going out of the battery is measured over time to calculate the relative amount of charge. It's like pouring water into a pot. The pouring water tank and it's fetching out to imagine the battery as a jar, and water is like electrical energy or charge. The BMS measures how much current is going inside the battery and calculates the charge deposited inside the battery over the time. When the calculated charge is near to the rated capacity of the battery, then the BMS informs that the battery is fully charged, and while it is charging, it follows the same process in addition to the both methods. The third combination one is the Coulomb combination of Coulomb counting and voltage measurement. In this, we will be approaching both the methods, and the next one comes the SOH determination. The state of health is the basic thing where we need to measure the health capacity of a battery when compared to the new one. Any physical parameter of the battery, such as internal resistance or conductance, changes significantly. The internal resistance of the cell depends on the impedance. As battery internal resistance of the battery increases, next comes the cell balancing. Cell balancing is a method to compensate the weaker cells by equalizing the charge on all the cells in the chain to extend the overall battery pack's life. In the whole battery pack, small differences between the cells are due to the tolerance of operating conditions gives rise to uncertainties. During charging, weak cells may get overstressed and become even weaker until they eventually fail, which causes the whole pack to fail prematurely. So to avoid this, BMS has to provide cell balancing. Cell balancing BMS also works as a logbook because the SOH of a battery is relative term. It compares the new and old battery. So this measurement should hold a record of the initial conditions of a cell and should able to compare with the same cell as it gets old. So the logbook function is the most important, and then the communication BMS provides the information about the health SOC along with much more details of service and maintenance. In general, user who is driving the vehicle is not a technical guy, so the information should be simple and interpretable. On the other hand, the BMS technician or an engineer is a highly technical guy, and he should understand each and everything regarding the BMS, and safety of the battery. Well, there are different types of topologies of a BMS hardware. It shows how we can connect these cells with a BMS first. The distributed topology, in this topology, there are small voltage and discharge monitor circuits which communicate with the master controller of the BMS. The advantages of this design is simple and reliable to implement, and as a highly reliability. The disadvantage of the system is it requires a large number of small PCBs and becomes difficult to mount on every cell. Next is the modular structure, and in this multiple slave VMs controllers are used to face the data and forward it to the master controller. So no special PCBs are necessary in this. And next comes the centralized topology, and it is a master unit is directly connected to each cell of the battery pack, and the controller unit protects the and balances all the cells. Using this topology decreases the hardware, but excess heat could be generated because the controller is the only source for cell balancing in centralized topology. Next comes the battery management system. It is made of many hardware and software functional blocks, which are the CFET, DFET, and fuel gauge circuit, cell voltage monitor, cell voltage balancing, and the technology behind each block is the cutoff FETs. In this, the technology basically transistors, mostly MOSFETs are used. MOSFETs are nothing but the control switches. These are used for connections and isolations of the battery pack between the load and the charger. Switches these FETs. These can be configured as here it is a single connection to the charger and load. In our case, motor controller, and generally first configuration is used for charging where just one bus control the initially both MOSFETs are turned off. When a charger is connected, flowing both FETs off. BMS sends the voltage as the input, then it turns the CFET. If the voltage or input in is not present, and it turns on the CFET, which charges the battery. If the voltage at the input pin is not present, then BMS determines that motor is connected. This block keeps the track of charge coming in and going out of the battery pack. For measuring the current, a current sense amplifier and a MCU which has an analog to digital converter is used. A very low current sense resistor is connected in series. The voltage drop across this resistor is measured by this amplifier, then it amplifies the signal. The microcontroller measures the voltage and calculates the charge according to the time. The discharging and charging current is sensed by the direction of current. If the current is coming inside or going outside, that means the battery is charging, or there are certain fuel gas ICs are available in the market which takes care of the SOC, and many times using a fuel gas IC add additional cost to the BMS. In case of electric vehicle, using a shunt resistor is always the best option. The fuel gas Next comes the cell balancing. Generally, lithium-ion batteries are used in EVs. The voltage of a lithium-ion battery ranges from 2.5 to 4.2 volts, and it depends on the battery chemistry. As we saw last time, operating the battery outside the environment reaches the most lifetime. These cells are connected in series or in parallel. The nominal voltage and temperature imbalance will slightly uh, differ from each other. So this weak cell heats up and its lifetime gets reduces. The weaker cell trips the discharge limit first, leaving the rest of the remaining cells charging remaining inside the same. This can be overcome by cell balancing. This cell balancing is derived into two parts. The first one is the passive cell balancing, and the second one is the active cell balancing. In this method, a dummy load like a resistor is used to discharge and equalize it with other cells. These resistors are known as bypass resistors. Each cell connected in series in a pack will have to undergo a MOSFET connected across. The weaker cell is turned on, the charge of this cell is removed and dissipated. This process minimizes the charging rate of the weaker cell. Whenever charge goes, the weak cell tends to go near to its full capacity. The MOSFET is turned on. So all the cells along with the weaker cells charges at the same time, but this method is not useful. The weaker cell may reach to its minimum cutoff voltage earlier than the other cell, but is not easy because it is very efficient, because electrical energy is dissipated as heat and has switching losses. Another drawback is that the entire discharge current flows through the MOSFET, which is mostly built into the controller IC, and hence the discharge current has the lower value to the IC's limit, which increases the discharging time. Active balancing, unlike passive balancing, is active. In active balancing, the excess charge from one cell is transferred to another cell which has low charge. So this can be done by charge storing components like capacitors, inductors. Well, there are many methods to perform this. Let's discuss the method which is commonly used. The charge shuttles or flying capacitor is the most commonly used method. In this, the capacitors are used to transfer the charge from high voltage cell to low voltage cell. The capacitor is connected through SPDT switches. Initially, the switch connects the capacitor to the cell which has high voltage, and once the capacitor is charged, then the switch connects into the cell which has lower voltage and the charge from the voltage to the cell. These capacitors are called as the flying capacitors. Well, the problem with this method is that the charge can be transferred only between them. Also, still it is better than passive. Just like there are many active cells balancing techniques, which are one of this is this one. Next important parameter is the temperature monitoring. Lithium-ion batteries provide a lot of current. So while maintaining a constant voltage, which can lead to a thermal runaway, causes the battery to catch up fire. The construction of battery is highly volatile. Well, this temperature measurement is just the temperature of the battery is suitable for charging these batteries, and the temperature sensors are used in general. The thermistor is basically a temperature dependent resistance. Whenever there is a change in temperature, the BMS calculates the temperature rise accordingly. As we saw, the BMS acts as a logbook to calculate the state of health and parameters of the battery. So for that purpose, the BMS has to take the data time, so it should be working even if the vehicle is not on run. Excess power from the battery pack itself. So to avoid that, a real-time clock is integrated, which needs a small power, and it does the job. Well, that's all about the battery management system of an electric vehicle.
Hello everyone, this is the continuation of the part 2 of battery management system, which was presented by myself Manikanta, and this video series is going to continued further by Ekta Chirde, Avinash and Parikshit, and I invite Ekta to discuss about the battery. Over to you, Ekta.
Okay, thank you, Mani. So when we come to battery, as we know, it is an electronic device which stores the energy and convert chemical energy into electrical one. So in this video, I will talk about the types of batteries and its properties. So there are various types of batteries, and in order to model that battery, we have to select. The battery is the most crucial parameter or the factor. So in order to get in detail with the types of battery, there are various types of battery primary battery and the secondary battery. So in primary battery, as we known for primary cells as non-rechargeable battery and the secondary cells as a rechargeable battery. So in primary cells, it is the dry cells actually. At the center, there is a carbon rod, where the outside of that carbon rod, the manganese and the ammonium chloride, this is the powder mixture. It is coated with around with this carbon rod. Now at the top, there is a metal cap which gives the positive electrode, and at the bottom there is a negative electrode. So this is also called as the dry cell that we generally use in our houses and homemade purposes. Now the secondary battery. So secondary cells are the rechargeable battery that we can recharge it. So that secondary battery, in secondary battery, there is some lithium ion batteries we can consider in secondary battery that we can recharge. So there are some battery chemistries I have to mention here. Like in primary cells, we have the lead acid battery that we consider in primary cell, the lithium air battery, magnesium battery. So those are all comes in the primary cell. But in secondary cell, as a rechargeable battery, there are some others battery like the aluminum ion battery, carbon battery. Again, in carbon battery, there are two types: single carbon and dual carbon battery. In lithium ion battery also, it comes under secondary, like lithium ion cobalt oxide battery, lithium ion manganese oxide battery, lithium ion polymer battery. So there are various types of batteries or chemistries comes under the lithium ion battery. So which those all are comes under the secondary cell. Again, gel battery is there. That is the uh, gel battery having some scope 2 days future. So gel battery generally it is a lead acid battery with the so this sorry this gel battery is the lead acid battery which with the jellified electrolyte, and in that the sulfuric acid is mixed with the fume silica, so which gives the gel like immobile. So this is the gel battery. Now over to when we comes to another battery types like swappable battery. So in swappable battery, first I will give the definition for swappable. That swappable battery, that means the exchange the drain batteries with the fully charged batteries. So this is called the battery swapping, and it is done in the exchange station only. So it is commonly used in warehouses using the electric forklift trucks. Now, when we come to this swappable one, like in general, the battery charging requires the long time. So it may be for electric vehicle or for hybrid electric vehicle. So thus for that, due to some policy or money or infrastructure constraint, they are not widely deploy this swappable battery. So in short, customers have to wait to recharge that battery. So the battery swapping can provide the fully charged battery, which does not require the depleting energy of older one. Then so you can see in battery swapping, like I have given the general overview here for the main components. So we can see here the structure, like for example, if we have the Tesla BSS as a case study, so it consists of a mechanical and structural components as well as electrical also. So in that Tesla vehicle, that there is a vehicle lift, battery lifts, vehicle alignment equipment, rollers, electrical connection alignments, battery conveyor shuttles, battery storage racks, and rails. So all these are comes under this battery swapping when we have to structure it. Then you can see here the EV battery swapping structure based on the battery swapping van. Now here the application of battery swapping van brings a clear change to EV battery swapping, like the specific function of each participant and the roles they play will be consequently changed. So in order to reduce that impact or in order to reduce that changes, so and provide the better efficient EV battery swapping, so we need to give service, or we need to give the function and role like each participant, that we have to change the structure of the battery, and so there are some specific process for this battery production, like charging, transportation, storage, swapping, communication. So all are comes under this battery swapping system structure. So after that, there are some specification for battery package, like the battery power capacity. So firstly, I will introduce that batteries are specified by the three main characteristics, like the chemistry, voltage, and specific energy capacity. So if we have gone with this first power capacity, so the power capacity means the nominal voltage of the battery multiply with the current in ampere of the battery. That will give the power capacity. And power capacity will have the units like ampere, kilowatt hour. Then after that, storage capacity. So from the power capacity, we can find out the storage capacity. Again, there are something specific energy also there. So specific energy or energy density, both are the same, which gives the battery capacity in weight, like watt-hour per kg. Again, from the specific energy, we can find out the specific power. So it indicates the loading capability of that battery. Then also batteries for power tools are made up of high specific power and come with the reduced specific energy. Now, for example, if we give the if we have the water in the bottle, so if we pour that the water bottle containing that water, that is our specific energy in watt-hour per kg. So when we pour that water in the bowl or in the glass, so this will comes under the specific power. That means this is the specific power when the water pouring into the glass. Then we can calculate the C rating. C rating means the speed of battery, that is charge or discharge, the present discharge or current discharge or charge the battery. Like there are some 1C rating, 0.5 C rating. So all these are rating given in the battery specification. Now the state of health and state of charge. So state of health, firstly three main state of health indicators of battery are like capacity, that is the ability to store the energy. Then internal resistance, that means the capability to deliver the current. Then self discharge, reflecting mechanical integrity and stress related condition. After that, state of charge. So state of charge means firstly state of charge which reflects the battery charge level and reading the battery user is most familiar with. So SOC fuel gauge can create the false sense of security, as good and faded batteries show 100% when fully charged. Now when we comes to regular battery, so I have considered here the CG R17500, that is the lithium ion battery which is normally used in our vehicle. And this CGR 17500 lithium ion battery generally this is developed by the Panasonic company. So this battery consists of this battery having the chemistries LiCO2. So in this battery that there are two electrodes, positive and the negative. So positive electrode is the LiCO2 and the negative one is the graphite, that is LiC6. So, and the electrolyte of that lithium ion battery consists of the salt which are dissolved in an organic solvent. Now it is it having the cylindrical structure with the diameter 17 mm and the height 50 mm. So some reactions are there to calculate the electrode reactions are there for that, like the for charging and discharging the battery. So that's it from my side, and the next part will discuss by Avinash. Over to you, Avinash.
I I am speaking about power source. Power source may be supply of electricity which we will be getting from, and actual main power source for us provided by electricity board is three phase and single phase power source. And coming to the three phase and single phase uh, power supply, generally the phase in the electricity uh, is the current or the voltage among the wires, and it contains a neutral cable also. and Phase is a distribution of load in a single wire or single wire if it is used in a single wire and neutral, it is called single phase. And if it is if we use three wires or four wires for a three phase system, and both supply AC power only. And coming to the main power source, we can get power from thermal plants like uh, coal thermal power plants, and nuclear power plants, hydro power plants, wind power and solar power. At plant, the maximum power produced by the turbine will be 30,000 volts. It will produce power up to 10,000 megawatts. The power plant will not go, the turbine will not generate more than 30 kilowatt, because the insulation coating of the internal winding will be too thick. That is why it is limited to 30 kilowatt. And from power plant, we will be producing 11 kilowatt to 30 kilowatt power from the generator of turbine power generation. And then from there, it will be transformed to the transformer, step up transformer. It will step up the voltage uh, at the power plant only. And then it is step up because to carry the um, current in less number of cables. If we are supplying 1000 megawatt and that 30,000 volts, the ampere rating will be very high. Now we can for transferring that amount of ampere current, we need so much of so many bundles of electric wires. That's why we will be stepping up the voltage and reducing the ampere rating, and we can transport the electricity within the limited electric wires. And from the power plant, there will be three phase line coming out, and from there there will be a substation. There will be in substation there will be a step down transformer. Again, it will reduce the voltage and distributed, and it is distributed to the large scale consumers. And then again it is going to it will be going to the households. At households there will be a transformer. Before going to households, there will be a primary distribution will be for medium customers. It will be around 7 to 33 kilowatts. And secondary distribution will be our households on commercial distribution. It will be of 440 volts. It will be a three phase wire. And if we take one wire from that and one neutral, then it will be a single phase. If we want, if the load is high, then we can take three phase. if we want more load, three-phase will be preferred. If not, up to 7 kilowatt or 7.5 kilowatt, one phase is enough. Beyond that limit, we need to use three-phase system. And coming to the materials used for the transmission electricity. Electricity lines is copper, aluminum, cadmium, copper alloy, phosphorus, bronze, steel core, aluminum, and steel core copper. Copper and aluminum, steel core aluminum will be used more because aluminum is very less weight, and copper is high tensile strength. Copper will be having high tensile strength. And coming to the electric vehicle equipment like charging stations, there will be a supply of electricity from the charging stations. There will be a DC charging stations and AC charging stations. In AC, there will be direct current will be transferred to the vehicles by the means of electrical vehicle supply equipment. And into the AC charging, there will be two types: normal AC charging and fast AC charging. And in normal AC charging, the rating will be power rating will be around 2.5 to 3 kilowatt. And in fast AC charging, it will be around 7.5 to 22 kilowatt. And coming to the DC fast charging, there will be two types of the level 1 and level 2 type of charging. In level 1, we will be using 48 volt and 72 volt system, which with a power of 10 kilowatt and 10 kilowatt to 15 kilowatt. At a maximum current we are using for this system will be 200 amperes. And coming to the level 2, it is used for high rated battery vehicles like Tesla vehicles and Nissan Leaf. It will be, the voltage is up to 1000 volts and power rating will be 30 kilowatts to 150 kilowatts, and maximum current rating will be 150 amps. And coming to the chargers, there are AC types of chargers and the DC type there will be different types of chargers. And coming to the AC plug connectors, there are in India we will be using IEC 6030 for e-carts and some Mahindra E2 vehicles and e-rickshaws. And normally, as per the standard, type 2 is used for so many all of the electrical vehicles in Bharat as per the Bharat regulations. It's IEC 62196. And a 3-pin connector is also used for normal electrical scooters. It is for the AC plug connectors. And coming to the DC plugs, there will be CADMO connectors and CCS connectors and GB by T connectors. In India, more it is as per the regulations, thinking to work on GB by T connectors. And CADMO connectors are also used for high power battery vehicles for fast charging. This is related to the power source. And now Parikshit is going to say about the loads.
So there are three types of loads used in electric vehicles. Means there are resistive load, inductive load, and capacitive load. So in resistive loads, there can be headlamps, fog lamps, inverter, then different switches such as relay switches, or you can say your normal switch to means for the to light up the headlamp or fog lamp. Then wiring harness, as you know, wire has a specific resistance. Each type of wire has a specific resistance. Then in inductive load, there are traction motors, AC compressor, windshield wiper motors, steering motors, and power windows. So as you see, motor is an type of an inductive load. So mainly there are around 5 types of motors used in electric vehicle. So first is DC series motor, brushless DC motor, permanent magnet synchronous motor, three-phase AC induction motor, and switch reductance motor. Nowadays, we means most of the vehicles are using brushless DC motor and permanent magnet synchronous motor. Then there is capacitive load. In capacitive load, three types of load are there: infotainment system, ultra capacitor, and door lock system. As you see, infotainment system, it has a screen, and we can play music and other entertainment things we can do with the help of infotainment system. And so it has capacitive load, as it has screen and other components also. Then ultra capacitor, as you know, means when vehicle required high power, or means it required high speed at for the certain amount of time, we used ultra capacitor. What we do, we charge the ultra capacitor for time while, and then when we require high speed or high torque, we use the ultra capacitor for the vehicle. It provide high voltage and high current to the motor. Then there is door lock system. It also used in capacitive loads. So these are the general loads used in electric vehicle. So thank you for listening our present our poster. Thank you so much.